Okay, so let's start. So turn on video, if you can. And again, I will give you 0.5 bonus credits if you turn on video. And also, if you ask good questions during class, then I will give 1 bonus credit. I haven't updated that bonus credits for the last lecture, but I will do it after. Okay. Yeah. And the two small announcements. The first, chapter 4, the quiz, the 8.4 quiz, chapter 8, number 4, it has some error. So actually, it should say the O sub 3.1 and E sub 3.1, but I wrote the O sub 1.3 and the O sub the E sub 1.3. So I fixed it already. But if you are confused and you got the wrong answer, I will post a new question after the class, so you can still get points. And if you have already got full credits, then you don't have to answer the new question. Okay, and okay, Rihanna, Claudia. Okay, and the for final project plan, I think it's due on this Friday, I think. So I will prepare the form to submit your plan, and also another form to submit either CSV or Excel file. So yeah, it will be available soon tonight. Okay, so okay, so 1, 2, 3, 4, 5. And parser and skin. Oh, and the for late submission for Stat 5030, I have just uploaded the scores. So sorry for the delay, but now I graded all late submissions. I think I got one question. Is there something wrong with the quiz 86? The p-value got was about 0.001, which when rounded to nearest hundreds, it's 0. Yeah, I will double check, but the yeah, 8.6, maybe I will. 8.6 is what? Let me see. The quiz 8.6. I got a question on quiz 8.6 and okay. Let me see. Quiz 8.6 is what? That is 2 questions later than that. So the Fisher exhaust test. I don't think the p-value is that small. So maybe you can double check. Yeah, p-value isn't really less than 0.01. Okay, so that's it. And another question. Oh, okay, so maybe parser asked question, and the another question. Oh yeah, you're right. And the another question. So would you be able to go over the solutions for quiz 8.1? Quiz 8.1. What is quiz 8.1? Quiz 8.1 is okay. So question about simulation of the binomial distribution. In R and calculate probability of sample proportion of 0.55 or less. Yeah. Okay, so let me see, just a moment. Yeah, I will upload the solutions after the class, but I think the single proportion and the you upload. Okay, so 8.1 is due on, okay, so last time, so that's fine. So I will share the screen to discuss. And I think that this is the question. So we generate the, okay, so simulate 200 observations of the binary random numbers whose value is 1 with 60% probability and 0 with 40% probability, and calculate the proportion of ones and repeat the simulation 100,000 times. And how many times does the proportion is smaller than 0.55? So if our survey size is 100,000, and the true probability is 60%, then what's the chance that we have less than 55% as the sample proportion? Yeah, and this is the code. So we generate the binomial random variable with the 200 observations, the 100,000 times. So this is the simulation for 100,000 times. And each time we simulate the 200 observations. So the proportion is this number divided by 200. And then we get the 100,000 results. And we take the number of times the x is less than 0.55. And my answer is the 6,562 times out of 100,000 times. So that is about the 0.65%. Yeah. But yeah, anyway, so the answer should be something like that. Actually, another simulation, I got the 6,557. Yeah. Yeah, you can actually use the theory to answer these questions as well, but the question as well. But this is what I intended you to do. Okay, and now we stop sharing, and yes. Okay, so I will go to chapter 11. Yeah, so chapter 11 we are doing. So the chapter 11 is about multiple linear regression. So the assumption is that the response variable is continuous. For example, the price or log price of condominiums. And the predictor variables, we have multiple predictor variables. For example, in this example, that we have the square footage of condominium and the year built of condominium and the number of bedrooms in the condominium and the number of bathrooms of the condominiums. So we have the 4 possible predictors. And you can see that all variables have positive association with price. So our natural thinking is if we combine these information, these pieces of information, so the number of bedrooms, bathrooms, square footage, and year, then we can have a better, a model to explain price. So how to combine these pieces of information. So that is our question today. And last time, just we discussed how to, present the data. But this time that we want to develop a linear regression. And today that we discuss more conceptual things. So rather than the example that we have more theory. And at first, the multiple linear regression model, it assumes the y is a linear combination of predictors and intercept and plus error. So in simple regression model that we don't have these terms, right? So the beta naught plus beta 1 x1 plus epsilon, but this time that we have the multiple predictors, and our assumption is y is a linear combination of the beta naught to the intercept and x1 to xp. And epsilon is an error, so we assume that that is independent and identically distributed. And the expectation of epsilon is 0 because this is error term. So on average, it should be 0. And often we assume that the epsilon follows the normal, the 0 sigma square for many of the results, such as the so the t-test or ANOVA, that we need this assumption. But in general, for some results, this isn't really necessary assumption. So I didn't specifically write this assumption. So some results on multiple linear regression needs this assumption. Yes, and okay, so we have the data set. So we observe y, maybe the price of condominium, and the x1 to xp. Maybe in the previous example, maybe p is equal to 4, and the x1 is the square footage, x2 year, x3 the number of bedrooms, and x4 the number of bathrooms. So we observe the data for n observations. If we have 50 condominiums, then we have 50 observations of y and x1 to x4. So if we use the index for that observation, we can write the y sub j is equal to beta naught plus beta 1 times x1j plus beta 2 times x2j, and so on, and epsilon j here. And j is equal to 1 to n, where n is the sample size. So this, for example, this one is the second variable, but the jth observation. So the jth observation of second variable. Yeah, so this is our setting. Yeah, so example is just the example that I discussed earlier. So house prices. So we want to predict the house price by the square footage and year built and the number of bedrooms and the number of bathrooms. Yeah, so this is what the municipality does to calculate property tax. So they consider the square footage and the year built and the number of bedrooms, bathrooms, to explain the actual value of houses. So actual transaction price really depends on the house. Right? So sometimes the people want to make a trick in taxation to have artificially the low price or high price. So the city has to calculate the appropriate price for each condominium or houses. So this kind of model that they use. Maybe also they consider other factors such as the distance to the major highway and maybe this distance to I don't know, there's some other maybe schools or something, and something like that. In my city, when I looked at data, if houses are close to the major road, then assessment is much lower than other houses. So actually the actual price is also slightly lower, but the city has even larger discount on the house values. So if you want to pay less tax, then probably it's good to buy a house near a major road. Okay, so at least it has some applications. And something I want to mention. So the number of bedrooms and the number of bathrooms. These may be numeric variable, but may be factor variable. Right? So suppose that some houses have the number of bathrooms equal to 0 and 1 and 2 and 3. And we have 4 possible values, but okay, this is a kind of numeric, but we are not sure if the additional bathroom has the same, the additional bathroom to the two bathrooms has the same value as the single bathroom, right? So the difference in house price between 0 bathroom and 1 bathroom may not be the same as the difference in price between the 2 bathrooms and the 3 bathrooms, right? So in that way, these numbers may not be numeric. You are thinking about it. So if these are not numeric, then we have to consider these as factor variables. And the factor variables means that each possible value represents the one variable. Okay, so maybe I would like to explain with more concrete examples. So suppose that, for example, we have data set such as, okay, so we have price. So price is, okay, so maybe 200K and the 350K, maybe 310K and 400K and the 500K or something. Then we have maybe the square footage. We have the, okay, so square footage of, maybe this is the, maybe 1000K. And the square footage we have, okay, so 1,510 or maybe 2,050 or something like that. So 1,850 or 3,010 or 3,140 or something like that. Then suppose that the number of bathroom is, here it's 1, and here it's 2, and here it's 2, and maybe 3 and 2 or something like that. Then in this case, the one way to define y and x1 and x2 is just we define this. Okay, but if the number of bathrooms is not really a continuous variable, just we have to see these 3 as different factors. So in such a case, that we fit the model with price and square footage, these are the same, but the number of bathrooms, basically, we want to prepare the factors for 1 bathroom and the 2 bathrooms and the 3 bathrooms. So the data should be put as the 1 0 0 0 0, the 0 1 1 0 1, and the 0 0 0 1 0. So here, this is the indicator variable for 1 bathroom. And this is the indicator variable for 2 bathrooms. And this is the indicator variable for 3 bathrooms. And you have to fit the price on intercept and the square footage and the plus actually each of the variables. So I would say that the beta, maybe I would say the beta 2 of the indicator variable of bathroom 1 and the indicator variable of bathroom 2 and indicator variable of bathroom 3, something like that. So we have literally the more variables. But actually the one thing we have to be careful is that if we consider these 3, the sum of these 3 variables, this becomes always 1, 1, 1, 1, 1. And this is the same as intercept. So we have trouble to include the intercept and these 3 variables because these are linearly dependent. So that means we have multiple solutions. So if we make beta naught one larger, then we make the beta 2, beta 3, beta 4 one smaller, then actually the right-hand side is exactly the same. So that means that these parameters are not identifiable. We don't have a unique solution. So we have trouble about that. So we have to actually reduce the one variable. So in this case, maybe we should have some baseline, maybe this as a baseline. So we have to eliminate this part, and we have to fit the beta naught. Beta naught is a kind of the baseline price for the one bathroom. Okay, and then this is just as is. Then beta 3 represents the difference in price. I mean the value, the additional price for 2 bathrooms. So compared to the one bathroom, so we have the beta 3 higher value if we have additional bathroom. So maybe to be exact, the this is the difference, basically the expected the price for 2 bathroom minus the price for 1 bathroom. Okay. And the beta 4 represents the price for 3 bathroom minus the price for 1 bathroom. So we have to interpret in this way. So if we include these 3 factors, beta 2 bus 1 and beta 3 bus 2 and the beta 4 bus 3, then we have trouble to identify parameters. So we have to prepare baseline, and we should remove this term to make the model work. So in this case, okay, so if number of bus, okay, so actually in real data set, we have other variables and year and number of bedrooms, but just ignore that, those variables for now. And if we have square footage and bathrooms, if the number of bathroom is numeric, so we have the literally 2 predictors, right? So 2 predictors. Maybe if we add intercept, then we have 3 parameters. If including intercept. But if the number of bathroom is factor, that we have actually the 4 predictors. Maybe you can say 2 predictors, but mathematically speaking, we have the 3 predictors, because this one and this one and this one. So we have the 4 parameters including intercept. So we have the different numbers. If we have more categories, if number of bathrooms is either 1, 2, 3, 4, 5, then actually we have the 4 terms for bathrooms. So we have the 5 predictors and 6 parameters. So the multiple linear regression that works in this way. So if everything is continuous, you can interpret just one as is. But if some predictors are factor variables, then mathematically speaking, we have more predictors. So, and yeah, sometimes we say this as the design matrix or model matrix. So this part. Maybe some people remove this column and say the remaining 3 columns as the design matrix. or model matrix. Yeah. I got a question. Wouldn't we have a more accurate model with a separate linear model for each value for the number of bathrooms? Yes, so that's the reason for introducing this factor variable. Yes. So if the relationship between the number of bathrooms and the price is the same, then probably it's better to make it as numeric variable. So maybe one additional bathroom that we always have the $30,000, then that's good. But if the relationship between the number of bathrooms and the price is not linear, then certainly it's good to use it as factor variable. For example, one bathroom has the baseline price, and 2 bathrooms, we have maybe the $40,000 additional, but the third bathroom only add value of maybe $15,000. So that is a possibility. And in such a case, the factor variable is better. And this is actually the pretty difficult case, whether we should make it as factor variable or a numeric variable. Yeah. For example, if the predictor is obviously factor variable, we have to include it as a factor. For example, the type of house, we have the colonial and maybe ranch and bungalow and what, maybe the tri-level or something. And those 4 are clearly factor variables. So that we have to include it as factor variables, but the number of bathrooms is still, the number makes sense. So it's really hard to decide, but in some case, the number of bathrooms as factor variable, that makes more sense. Yeah, so if factor variable, the relationship between y and x is more flexible. So each level of x has its own level of y. For example, the price difference between the 1 bedroom and 2 bedrooms may not be the same as the price difference between 2 bedrooms and 3 bedrooms. Yep. Okay, so now, do you have any other questions? Okay, so maybe I will check the attendance. So just a moment. What should I? Not sure. Participants. Sorry. Okay. So now that we go to more mathematical part of the section. So remember that we have matrix representation for simple linear regression. So that was the y is just this shape, and the x was just the first 2 columns of this matrix. But now we have the p variables. So we have larger x. So in this case, we have p variables. So x is n by p plus 1. So some people prefer to make the number of variable as p minus 1, so that including the intercept, it's n minus p, but here n minus p plus 1. And beta is the p plus 1 dimensional vector, and epsilon is n by 1 again. So I would say p plus 1 by 1 matrix. So then we can write this relationship, the equation as y is equal to x beta plus epsilon. For example, the y1 is equal to the 1 times beta naught plus x11 times beta 1 and x21 times beta 2 up to xp1 times beta p and plus epsilon 1. So you can see that this as y is equal to x beta plus epsilon. So this is matrix equation, n plus 1 dimensional matrix equation. Okay. And yes, so yeah, so that's the matrix form. So it's actually as simple linear regression. So that is the biggest benefit. So if we have only single predictor, then matrix form may not be necessary. But if multivariate case, this expression is much easier than original equation in the previous page. And how to estimate beta naught to beta p? That has also the same principle as simple linear regression. So to estimate these values, the beta, we minimize the sum of squared errors. So we minimize the sum of epsilon j square from j is equal to 1 to n. And that is written as this. And this is a function of beta naught to beta p. So we can minimize this value. And this is actually the quadratic equation of beta naught to beta p. So if we take the derivative and so on, actually we can derive the analytical solution pretty easily. So this is just a linear system. So you can review the chapter 6 to see the proof. The proof for this formula beta hat is equal to x transpose x inverse x transpose y. So we can apply the theory in the same way as simple linear regression. And the formula for y hat and the formula for epsilon hat and the formula for variance of beta hat and the definition of adjusted R square and the prediction interval, confidence interval, those are obtained in the same way as simple linear regression. So primary reason is that anyway, we have this expression. So the theory applies in the same way. Yeah. So that's the basic principle. Or maybe I have to mention one more thing. So sometimes the multiple linear regression has difficulty to see what's the contribution of predictor 1 and predictor 2 and so on, because we just minimize the error, right? So we don't really distinguish the contribution of x1, x2 up to xp. So as long as error is minimized, that's fine. So sometimes it has some difficulty to identify which variable is more important or has more contribution to y. Yeah. Especially, for example, if x1 is very close to x2, then the x1 plus x2 and also maybe 2x1 and also 2x2. So these three are very similar quantity. So actually it's really hard to distinguish the contribution of x1 and x2 to y. Yeah. And also, yeah. So that's the case. So just the linear regression focuses on minimizing error, but not focusing on explaining the contribution of each predictor. So we will discuss it later in detail. But yeah, that's the basic algorithm for linear regression. And also yeah, so here I would like to justify why we have to minimize this quantity, the sum of squared residuals. Yeah, so the one answer is, okay, so just we define this as is. But I would like you to understand that this has some theoretical justification. And if you know that, then when you study more advanced models, such as the generalized linear models, you can see why those model should be sorry. Then you can understand how to estimate the parameters for more general models. So for example, the people in other fields, the more like the the social science or humanities, okay, so they still study regression analysis, maybe also engineers, but our course is in mathematics department, so I want you to understand the theory behind it so that you can generalize the idea. And here, the fact is that this least square estimate for parameter beta is a special case of maximum likelihood estimator if epsilon j's are IID normal. So here, I officially add assumption of epsilon j is independent and identically distributed normal random variables. And the likelihood estimator, maximum likelihood estimator, has the many good properties, such as the asymptotic consistency and asymptotic normality and the unbiasedness. And yeah, so it has basically the best type of estimator in statistical estimation. And actually, this least square estimator is the same as maximum likelihood estimator if we have this assumption. I wonder how many of you have already heard of maximum likelihood estimator. Maybe if you have taken 5800 already, then I think you should have studied it. But otherwise, I'm not very clear. Sure. But here, I would like to explain the notion of maximum likelihood estimator. And this is, okay, so just a kind of small toy example to explain the concept. So it's not related to linear regression, but just I focus on explaining the idea of maximum likelihood estimator. And okay, so consider the situation that we randomly pick up a die out of the 3 dice, X, Y, and Z. And the X, Y, and Z have different properties. So actually these dice are kind of the loaded dice. So the probabilities are not the same for the 6 faces. And actually the X is the usual die. So the probability of having the face of 1 is 1/6 and face of 2, 1/6, and so on. But the die Y has different probabilities. Actually, the highest probability, the high probability of getting 1, actually the 50% of the time, it landed on the face of 1. And the 2 to 6, the probability of is only the 1/10, so that the total probability is 1. So I would say that total probability is always 1, right? And the die Z is more likely to be 2, but the also higher probability for 1, and the very low probability for the 3 to 6. And still, the total probability is 1. Okay? So we have different dice, but you pick up 1 out of these 3, but you don't know which die that you picked up. So maybe 3 dice are indistinguishable when just you just look at those. But you know that if you roll that die, the result was 2. You didn't roll twice, but you just rolled it once, and the answer, the result is 2. Okay. Then which die is most likely? So that is our question. So okay, so we got the face of 2, and we don't know which die that we chose. But based on that information, we can compare these 3 probabilities and conclude that it's most likely that we picked up Z. Right. So that is the basic idea of MLE. So we compare this probability vertically. So that is a new idea, different from probability theory. So probability theory, so we always discuss the probability space, and this row sum up to 1 because the total probability is 1, and this row sum up to 1, this row sum up to 1, and we discussed that the X is uniform random variable on 1 to 6, and the Y is a random variable which has higher value, a higher probability for 1, and so on. Always probability theory, see this table horizontally, right? But the maximum likelihood estimation, we see this table vertically. So that is a new idea. right? And we compare these three numbers, and so this number is largest, so that we conclude that that is most likely Z, right? And that is the idea of the maximum likelihood estimator. So here, our die, if the D represents the die we picked, then the D hat is equal to Z. So that is our answer. And generally, we have multiple experiments. So we roll die maybe 10 times, and we get the maybe 1, 2, 3, 4, 5, 6, and if we roll die 10 times, then the frequencies are maybe the 1, 2, 2, 2, 2, 1 or something like that. Then even though but anyway, yeah. So then maybe the phase of 2 appears that twice out of 10 times. So that is slightly larger than 1/6. But if we see these 10 observations, probably die X is more likely, right? So depending on the result, that you can guess which die is most likely, right? So generally, we have to have more complicated calculation if we have the multiple observations, but that is the method of likelihood estimation. And often, actually, the most of the time, so these possibilities are not discrete but continuous. So for example, we have a machine that to make maybe packages of maybe coffee or something, and that we don't know what value the machine is set to make those bags. And based on the package weights of packages, we have to decide how machine setting is determined. Then in such a case, maybe this unknown parameter to guess is maybe the setting of the machine, and that can be set at from maybe 0 to 1000 in continuous scale. So this scale is usually the continuous, and we have to determine which value is most likely. For example, if machine, we know that the machine is set so that they make the packages of maybe 450 grams, but we cannot observe it, and we only know that the machine is set at 0 to some value between 0 to 1000, and we get several samples, maybe 440, and we have 540, and we have the 490 or something like that. Then out of these numbers, these obtained numbers, we have to guess the set weight of that machine, and then probably we have to take average of these three and to guess that our set parameter is probably around 490 or something like that. So that is the the procedure to get the maximum likelihood estimator. Okay. So in this example, the possible choices are X, Y, and Z, so discrete. So we have to pick the one of those values as the maximum likelihood estimator. Okay, do you have any questions? And now that we want to prove that under our assumptions, the least square method is maximum likelihood estimator. So yes. So in the previous one, so these are discrete cases, and also possible values are also discrete in this case. But usually the possible values is also continuous. such as these observed values. So in such a case, instead of this probability table, that we have to use the probability density function. So that is, the continuous version of the probability table. Okay, so our random variable is epsilon j, and our assumption is that follows the normal 0 sigma square. So the probability density function for epsilon is given by this 1 over sigma times the square root of 2 pi times exponential of negative epsilon j square over 2 sigma square. And if we observe n observations, then if these are independent, then the probability density function for these n observations is the product of these PDFs, and that is the product of this number. And we want to maximize these numbers in terms of parameter values, the sigma and the beta naught to beta p. And the maximizing f is equivalent to maximizing the log of f. Maximize the f and the maximize log of f, because the log is actually the hold the order of observations. So if a is smaller than b, the log of a is smaller than b, log of b. So these are equivalent conditions. So actually, to maximize f, basically we can maximize log of f. And if we take logarithm, the product becomes summation. So usually computation is easier. So basically, our objective for this case is maximizing this quantity, the summation of this constant minus the negative minus the log of sigma minus this quantity. And yeah, we want to maximize this with respect to parameter. So parameter is here sigma, and also remember that the epsilon j is equal to the yi minus beta naught minus beta 1x 1i up to minus beta p x pi. So this is function of beta naught to beta p. So we want to maximize this quantity with respect to the sigma and the beta naught to beta p. And you can see that this first term doesn't really matter. So this is constant. So it does not really matter for what parameter maximize this quantity. So we can just ignore it. And so we have only two remaining terms. So this negative log of sigma and the negative epsilon j square over 2 sigma square. And yeah, we have to take summation as well. And once we take summation, then we got, yeah. So yeah, and we want to maximize this quantity, right? So we want to maximize this quantity. So suppose that we have this as maybe g of epsilon or something, and we want to make the first derivative of this g. Because we want to maximize g with respect to sigma. And suppose this is sigma, and this is the y is equal to g of sigma. So this is function of sigma. Then at maximizer, the derivative should be 0. Right? So this is maximizer, sigma hat, which maximizes g of sigma. So I check the condition of this derivative of, maybe it's too small. So derivative of the g sigma is equal to 0. And that is this equation. So log of sigma becomes the 1 over sigma. So here, the 1 over sigma here. And we take summation over j is equal to 1 to n. So we have n here. and the 2 times sigma squared, the inverse, so 1 over 2 times sigma squared. If you differentiate it, that becomes negative, the 1 over sigma cube. And we have a negative sign already here, so it becomes positive of the 1 over sigma square. And we take summation of the epsilon j square, so we have here. Epsilon j does not include any sigma, so just it is as is. And if we solve this, then you can derive the sigma hat square is equal to 1 over n times summation of epsilon j square. So that is reasonable because this is a kind of the variance estimate, right? Variance estimate of the epsilon j. So that is the sigma hat square. So it's natural conclusion. Then, okay, so we maximized the quantity with respect to sigma, but also we want to maximize this with respect to beta naught to beta p. So how to do that? Then, okay, so we don't derive the exact formula, but basically, if we plug in this equation to this, then you can see that the, you can see that this part is canceled, right? So sigma square is basically summation of epsilon j square, and the numerator is also summation of epsilon j square. So basically it becomes constant and we can ignore it. So only important term is this negative of sigma. So if we plug in sigma square is equal to 1 over n summation of epsilon j square, that we get this number. So our objective is minimizing this number. But the maximizing this number. Maximizing this number is the minimizing the log of summation epsilon j square over n. And minimize this means the minimizing the epsilon j square, right? So that's why the minimizing epsilon j square is equivalent to the maximum likelihood estimator for the sigma and beta. So actually, under the normality assumption and the independent assumption, minimizing epsilon j square is getting the maximum likelihood estimator for beta. Yeah, and okay, so actually this is not super important if we only do linear regression with this assumption. But if assumption is violated, then certainly we have to make adjustment. Then you really have to know the fact that this is maximum likelihood estimator. So if the assumption is violated, basically we go back to maximum likelihood estimator and see how estimator should change. Okay, any questions so far? Yeah, and from now on that we discuss the more concrete code, R code for multiple linear regression. And the code for multiple linear regression is almost the same as simple linear regression. So we use LM function and the response variable here and the predictor variables connected by the plus symbol. So square footage plus year plus bed plus the number of bathrooms. And here tilde is the same. So actually, yeah, I think at least on Mac that we have 2 tilde symbols. And I think that if you copy and paste this to our session, probably you got an error. We have slightly larger tilde, so you have to replace it. This is the shift of the upper left button in usual English keyboard. And these are results. So we have the beta naught hat here, and beta 1 hat here, and beta 2 hat here, and beta 3 hat here, and beta 4 hat here. So you can see that the number of bedrooms and the number of bathrooms are regarded as the numeric vectors. If you make this as factor vectors, then you get the indicator, the coefficient of indicator variables for each number of bedroom and each number of bathrooms. And the output looks almost similar to simple linear regression. Oh, I got one question. Does this have the bathrooms as numeric? Yes, so it's numeric, yes. So, but if you want to do you want to make it factor variable, still the code is the same. Just the this variable should be factor. So you can say the as factor of bus. For example, that you make, for example, the BA variable as this, then you put BA, then just it works as factor variable. Yes, so it returns the standard error and the t-value and the p-value as well. Oh, actually, this may not be the condominium data, but this may be the another data set. Yeah, we have housing data. And do you know how many observations are there? Maybe difficult question, but so sorry, I got another question, so I want to answer that first. So how many predictors do we have to use multiple linear regression? At least more than one. Yeah, actually, the code is the same between simple linear regression and multiple linear regression. So the minimum is one. Actually, minimum is zero, actually. So you can fit the LM, for example, price for just for on intercept. So this is the minimum case, maybe. Yeah. One works as a predictor, but if other predictor exists, one can be omitted. So just this. Yeah. So any number of variable is fine. So been there. Okay, and we want to continue this slide. And okay, so how many observations are there here? Actually, we have 490 observations here. And you can see we have 5 parameters, right? So we basically lose 5 degrees of freedom after fitting this model. So we get the 485 485 degrees of freedom remaining. So actually we did the t-test. So this is based on the normality assumption of errors. And this follows the t distribution with df 485. So this is the t distribution with n minus 5, and 5 is the number of predictors. Yeah, so actually from this 485, yeah, you can get this information, and also we know that we can get we got to know that there are 490 observations. Yeah, I think that I have explained the adjusted R square in earlier chapter. Yeah, I think in chapter 6, we have discussed adjusted R squared and the multiple R squared. And actually, the adjusted R squared doesn't make much sense for simple linear regression case. But here, you can see that the adjusted R squared is lower than multiple R squared. And if we add more predictors, then this number gets lower. So basically, adjusted R squared penalizes the large number of predictors, because if we have more predictors, naturally, then we can explain more variation in Y. Yeah, and other parameters are interpreted in the same way. So this, the residual standard error, this is estimated sigma hat, and F statistic is whether this model is in total useful or not. So the null hypothesis is the Y is equal to constant, and the alternative hypothesis is our linear model. Y is equal to beta naught plus beta 1x1 up to beta 4x4. So the test result on this is here. And the p-value is very small. So overall, this model is at least more useful than assuming the all houses have the same price. And the one, I got another question. So if we have two predictors in multiple regression, what is the difference between the two-way ANOVA? What's the difference between two-way ANOVA and the regression with two variables? The difference is the whether predictor is continuous or factor variable. So in two-way ANOVA, the two factors are two predictors are both factors, right? And in this multiple linear regression, so these predictors can be continuous. So in that way, different. But actually the multiple linear regression can include the factor variables. So actually the multiple linear regression is a generalization of the ANOVA, one-way and a two-way ANOVA. Yeah, we can say. Yeah. Yeah, so if you study multiple linear regression, actually we don't really need the two-way ANOVA, one-way ANOVA, and so on. So actually for me, it is strange to study ANOVA, but I think historically the ANOVA has been developed first because it's easier to deal with. We don't have any continuous values. So that's why we have separated theory for ANOVA and the multiple linear regression. But mathematically speaking, multiple linear regression is a generalization of ANOVA. I got another question. So can we include continuous variables in two-way ANOVA? We don't say that as ANOVA. So ANOVA means that all variables are factor variables. So that is just how that terminology is determined. So essentially, all ANOVA are just the special cases of multiple linear regression. Okay, and the one remark on the testing on this. So for example, that we think about the result of this row. So the number of bedrooms is significant with p-value equal to 0.00548 and t-value here and the standard error here. So what does this mean? Actually, this p-value tests the hypothesis, null hypothesis of this against alternative hypothesis of this. So basically, the null hypothesis is price is explained by square footage and year and the number of bathrooms. And the alternative hypothesis is the number of bedrooms. It has additional information to these three predictors. So that is the hypothesis to test. Or formally, that we can say H naught is the assumption of beta 3 is equal to 0. And the alternative hypothesis is beta 3 is not equal to 0, assuming the nothing about beta 1, beta 2, and beta 4. So H naught still, the beta 1, beta 2, beta 4, there can be some non-zero values. Yeah, so this is a kind of the leave one out test. So the number of bedroom has additional information to other variables. So these results are very strong, right? So so all variables are significant. So that means that if one of these variables is missing, then suddenly the model is worse. So definitely we need all four information. Yeah, and it's interesting that and also it's interesting. It's important to interpret the output. Okay, so square footage, for example, this. So yeah, so this is square footage, the 1.09 times 10 to the power 2. So this is 109, right? So one additional square footage, the price is $109 higher. And year, so this is also the 778. So if the house is 1 year newer, then the price would be $778 higher. And again, the number of bedroom is the number of bedrooms is continuous variable here, and this has actually the very large negative number. So negative 8,837. Okay, so that means if we have additional bedroom, then the price would be $8,800 lower. Okay. Why? Because the square footage is given, so we know that the house has some square footage, like the 2,000 square feet. Then compare this 2,000 square foot house with 3 bedrooms and 2,000 square foot house with 4 bedrooms. Then 4 bedrooms, basically, the almost entire space is occupied by bedrooms. And we don't have expensive features other than that. For example, the bathroom or a large kitchen. So those are more expensive than just bedrooms. Bedrooms are just boxes. So that's why more bedrooms, the lower price. This sign would be different if we have no other information. If we don't have square footage, probably the number of bedroom have positive coefficient. So the interpretation is very tricky. And the number of bathrooms, this has very large positive coefficient. Actually 10,000, the $430. So one additional bathroom, basically the price is the $10,000 higher. That is understandable. So if you want to make one more bathroom in your house, probably it will cost the $10,000, around $10,000. Yeah, so in final presentation, it's really important to interpret estimates. So estimate, especially the sign of estimates are consistent with your intuition or theory or some prior information. Of course, if those are not significant, then everything can be possible. Maybe we got additional features such as, okay, so like the garage, large garage, maybe the additional garage. Then we have something, and maybe garage, maybe the maybe what maybe the basketball court or something like that. And probably that doesn't add much value to your house. And maybe the coefficient, suppose the coefficient is negative the 300 with the standard error 600 and the p-value negative 0.5 and the p-value of the 0.54 or something like that. If it's not significant, the sign does not really matter. But if it's significant, I think the sign should be consistent with the theory or other intuition. I got another question. Could the p-values of each of the predictors change a lot if we added more predictors? Yes, it changes dramatically. Yeah, so interpretation of these coefficients are really limited. So suppose that we have only 4 possible factors, then whether this factor is useful in the model. So we can only say that. Yeah. If you include other variables, then maybe you can get more accurate information. If you add more useful information, maybe some of this variable becomes insignificant. That is possible. Yeah, so we have also studied the use of ANOVA function in chapter 7. And the difference between ANOVA function and this multiple linear regression function is here. So ANOVA function tests variable sequentially. So at first, they test this hypothesis against this. So if no other information is available, then whether square footage is useful variable. Then we have higher chance that this is a significant variable. And the ANOVA function tests the this null hypothesis against this alternative. So suppose that the square footage is in the model. We have already considered the square footage of the house to explain price. Then whether or not the year built has additional information. So that is the next test. And we do the test sequentially. So the last test is this null hypothesis against this. So given square footage and year and the bedrooms, the number of bathrooms has additional information to Y, the price. So that is the last test. So we have slightly different meaning between the multiple linear regression output and this ANOVA result. Yeah, and the balanced two-way ANOVA, actually the two-way balanced the data with two-way layout, the leave one out test and the sequential tests are equivalent. Yeah, that is a special case. And for multiple linear regression, the two are not the same, so the order of the variable affects the result. So this is the ANOVA result. And at first, we see if the square footage is important or not. Second, the year is important or not, assuming square footage is already in the model. We test the number of bedrooms has additional information to square footage and the year. So this is p-value. And the number of bathrooms, this is p-value. And we can also fit the model in a different order. Number of bathrooms, bed, and the square footage, and the year. So in the previous slide, okay, so this is significant, but the p-value is 0.008. And if we put the number of bathrooms at first, then this number is very small. So less than 10 to the power negative 16 times 2.2. So of course, if we have no other information available, then number of bathrooms is certainly the best, certainly has very useful information. So suppose you have to buy a house only with the information of the number of bathrooms. So which house do you buy at the same price? A house with 1 bathroom or house with 5 bathrooms? We can easily guess that the latter house is larger and more valuable. So these p-values are different. So if the order is later, then basically p-value is less likely to be significant. But in this case, all p-values are significant, but still the relative size of p-values are different. Yeah, so these are the chapter 11.2. And maybe I concept Emily. Yeah, so that's it for today.